So our next speaker is Abhishek Saha from Manin University, and he will speak about the Manin constant and periodic bounds on denominators of the Fourier coefficients of new forms at cusps. So please.
Thank you for the introduction, and thanks to the organizers for inviting me to give a talk at this very nice conference. So everything I'll be talking about today is joint work with Kestutis Seshnavicius and Michael Neururer. So I'll start off by giving a quick, I'll start off by giving a quick overview on cusps of gamma naught of n. So any cusp of gamma naught of n, so any cusp of x naught of n, is equivalent to a rational number of the form A over L, where L divides n. So this L is uniquely determined by the cusp C, and GCD of A and L are 1. So we are going to I'm going to refer to L as the denominator of the cusp. So this is probably familiar to most people, but I just want to go over these basic facts before I set the C. One can check that there are exactly phi of the GCD of L and n over L cusps of denominator L. So what does this mean? It means that L is going over the divisors of n. So if L is equal to 1, then the GCD of L and n over L is 1. So there is exactly one cusp of denominator 1, and that is simply the rational number 1. Again, if L is equal to n, then you again see there are exactly one cusp of denominator n, and that is simply the cusp at infinity, which is equivalent to 1 over n. So these are the cusps, and my interest today is talking about Fourier expansions of new forms at various cusps. For the Fourier expansion, you might recall that it involves the so-called width of a cusp. So if you have a cusp A over L, then the width is explicitly given by n over the GCD of L square and n. The significance of this number W of C, the width, is that it's just the smallest integer, such that this equation holds that if you take a matrix that sends infinity to the cusp C, so any matrix of the form A, L on the first column would do, then if you normalize, if you conjugate 1 W01 by that matrix, you are going to end up in gamma naught of n. That's the smallest integer W with this property is the width of the cusp. And finally, it's useful to recall the well-known Atkin-Lehner involutions, which permute the cusps. So basically, if you have a cusp A over L, then there exists a family of Atkin-Lehner involutions, and they will take this cusp to possibly other cusps. But the thing is that it will take a cusp C to a cusp of denominator L prime if and only if the valuation of L prime is either equal to the valuation of L or equal to the valuation of n minus the valuation of L for each prime dividing n. So you can look at the exponents of primes dividing L, and what happens is that the Atkin-Lehner operators switch the exponent and valuation of n minus that exponent. So there are basically 2 to the power number of divisors of n, that many Atkin-Lehner involutions, and that's how they act on the cusps. All right, so that was a very quick overview of 3 facts on cusps that we will need. So now let me come back to the question that I'm interested in talking about today. So suppose you have a holomorphic new form of weight k, level coefficients AF of n. So I'm going to normalize this always so that the first Fourier coefficient is 1, as is commonly done. And then it's a well-known but fairly deep fact that all the Fourier coefficients are algebraic integers. That is a property of holomorphic eigenforms, holomorphic new forms. This is something that would not be true, for instance, if you were a mass form, but it's really the holomorphy is important here. So anyway, all the Fourier coefficients are going to be algebraic integers. In particular, there are no denominators in any Fourier coefficient. So what happens if I look at a different cusp? So if you now take some other cusp C, then you can write C as gamma acting on the cusp infinity, and then the Fourier expansion at C is simply you take f slash gamma and you write that out as the Fourier expansion at the cusp C. Here, you are going to have an expansion in terms of q to the power n over the width of the cusp, not q to the power n, so you can't have fractional powers of q. And remember that the width is some number that I defined in the previous slide. And these are going to be my Fourier coefficients at the cusp C. I should mention here that even though the notation is AF of NC, in reality, it is not really well defined. It depends not just on the cusp C, but also on the choice of gamma taking infinity to C. But this is fairly innocuous because different choices of gamma will simply mean that the Fourier coefficient is going to be multiplied by a root of unity. So for the question I'm interested in today and lots of other questions, you don't really worry about this too much. So my main question today I want to focus on is, what can one say about the denominators of these Fourier coefficients at C? So what does this mean? It means that even though they're algebraic integers at the cusp infinity, for a general cusp, they do not have to be algebraic integers. So one could ask, like, what powers of primes could come up in the denominators? It's still a little vague. So here is how I want to make the question precise. So if given any prime p, I'm interested in good lower bounds for what I call val p of f slash c, which is simply the infimum over all n of val p of af of nc. So I'm going over all the Fourier coefficients af of nc, so all the Fourier coefficients of f at the cusp c. I'm looking at the p-adic valuations of these Fourier coefficients, and I want to know how bad can I get, like what is the lowest possible value I would get. So here, val p is the usual p-adic valuation, meaning that over the integers, val p of an integer reaches the highest power of p dividing that integer. Over the rationals is the same, so highest power of p dividing the rationals. But now, in general, my Fourier expansions will be algebraic numbers, not rational numbers. So then there is a choice involved about extending the valuation val p to q bar. So what one can do is one can fix any isomorphism between C and QP bar, and then QP bar has a unique p-adic valuation, and then use this isomorphism to extend it to and use this valuation to extend it to the general case. Yeah, there's a question in the chat about coefficients being algebraic. Yeah, it's not obvious. Yeah, as I said, it's the fact that they're algebraic integers is not completely trivial. I think. I think you would have a proof if you want to proof. If we look at Shimura's book on Shimura's book called, what's it called? I think his book from the 70s, or I forget what it's called, Introduction to the Arithmetic Theory of something. There is a proof there. Yeah. And also in several of his papers. So you really have to use something about the holomorphic nature of these objects. All right, so moving on. This is my question I'm interested in. So let's see. So here is the question. You want good lower bounds for this val p of f slash c. So first of all, what happens at the cusp at infinity? Clearly, val p of f slash infinity is 0 because all of these are algebraic integers, and the first one is just equal to 1. So the valuation of 1 is 0, and everything else will have a non-negative valuation, so the infimum is 0. In other words, at Fourier expansions at infinity have no denominators. For in general, there is a very powerful thing which is useful for us, which is known as the Q expansion principle, which basically says that if you have any kind of holomorphic modular form, and it works for other groups also, then you have if the Fourier expansion at infinity lies in some ring R, then the Fourier coefficients at any cusp will lie in joint 1 over n and e to the power 2 pi I over n. So what this means is that if you take R to be Z bar, the algebraic integers, then at any cusp, the Fourier expansions can only have coefficients involving n or integer, or it would just basically involve powers of n or something like that. So what's going on here is that the valuation of the periodic valuation of f at any cusp will be forced to be zero if p does not divide n. So it's only the primes dividing n that we care about. At other primes, they don't occur in the denominators. All right. So now we are going down to the question of understanding the periodic valuations of the Fourier coefficients at C for p dividing n. There's one more case that is very easy to deal with, and that is the case when the n is square free. Because if n is square free, then there are these Atkin-Nenner operators that I mentioned, and using them, all cusps can be moved to infinity. That's clear from the thing I wrote earlier, that the Atkin-Nenner operators switch the exponents of highest power of p dividing n, and highest power of p dividing L goes to the n minus that. So if n is square free, then the exponent of p dividing n is 1. So any cusp can be moved to, the denominator can be forced to become 1 at all primes dividing n by using a suitable Atkin-Nenner operator, which is simply the cusp at infinity. And we already know how the cusp at infinity looks like. All the Fourier coefficients are algebraic there. So using that, you can easily check that val p of f at any cusp will be equal to minus k over 2 if p does not divide the denominator L, and is equal to 0 if p does divide L. So again, it's a very easy case. So the main question I'm talking about today is really interesting if p square divides n. So it's only at the primes of square dividing n is where something interesting could potentially happen. All right, for general n, nothing much seems to have been done in before. There exist some generic bounds due to Brand-Conrad that uses intersection theory on regular stacky surfaces, but they're not very strong. They don't really use a new form structure, so they work in more general, but they're not as strong as what I would need for my applications. And there are also some other issues, like there are some typos there which make some of the bounds incorrectly stated. And even if you correct them, you don't really get a strong bound. So this seems to be quite not really a well-studied question, though I think it's quite a natural one. So that's the one I want to case. Because of the Atkin-Nenner operators, it's sufficient to restrict to denominators L such that L square divides n, because you can always switch, remember, between the highest power of p dividing L and val p of n minus that. So you can always make val p of L between 0 and n, val p of n over 2. So just for simplicity, I'll state my results when L square divides n, but of course, you can state them in general. So that was a lot of introduction. So let me give you some examples so that you see what it looks like before we actually get to the theorems. So here is an example. Take the level to be 24, weight to be 2. So since the level is 24, 2 cube divides it. So it makes sense only to look at the primes, prime 2. So p will be 2. And here is a new form, q minus q squared plus q to the power 4, etc. That's the Fourier expansion at infinity. So now let me take the Fourier expansion at the cusp half. So here is a matrix that takes infinity to half. It's 1, 1, 2, 3. And what happens is that the Fourier expansion involves 1 over 6, and everything else is algebraic integer. So val 2 of f slash half is minus 1, because 2 divides 6 and 4 does not divide 6. Another example. Here I take a power of 3 instead. So n is equal to 2 times 3 to the power 5. And I'll take p to be 3. And again, it is k equals 2. So both of these are holomorphic new forms of weight 2 and rational Fourier coefficient. So they really come from elliptic curves. So in this case, I can check again that val 3 of f at 1 over 3 is minus 3. And val 3 of f at 1 over 9 is minus 1. So you see, we really do get denominators when you go to other cusps. And they, so far, they have tended to be negative integers. But here is some other interesting example now where they're not integers anymore. Let's take n to be 25, a weight 4 new form, p equal to 5. Of course, p has to be 5, because if p was not 5, there's nothing interesting that can happen. Take this new form, q plus 4q squared minus 2 cube, etc. Then if you do f slash 1051, then you observe that you have 1 over 5 times a Fourier expansion that involves some algebraic numbers. And in fact, these algebraic numbers all turn out to be divisible by a prime lying above 5. So the periodic valuation, in fact, in this case, turns out to be -half, because these Fourier coefficients are all going to be divisible by a prime lying above 5, which is valuation half. And this 1 over 5 have valuation -1. So -1 plus half is -half. So here we are starting to see some fractional answers. Another similar example, n equal to 7 squared. And again, if you work it out in the appropriate cyclotomic field, you're going to get the valuation to be -1/6. Yeah. By the way, feel free to stop me at any point or to ask questions if there's anything that's not clear. Or... Okay, I'll move on. Here is one last example before I move on. Here I take a fairly high power of 2. It's 2 to the power 8 times 3. Again, weight is 2, so it's coming from an elliptic curve. P is equal to 2. And here, since its n is 2 to the power 8 times 3, it makes sense to look at denominators corresponding to half, 1/4, 1/8, and 1/16, meaning that denominators to be 2, 4, 8, and 16. And for each of these cases, I wrote down what it looks like, and you can check again that the valuations are -6, -4, -2, and +1. So somehow you're getting a strictly positive valuation at denominator 16, which seems interesting that all the Fourier expansions there are actually going to be multiples of 2. All right, enough examples. Here's
may I ask a question?
Yes, please.
So you mentioned the applications. So why were you interested in this problem?
If you give me about 5 minutes, I'll talk about the main application. It involves elliptic curves.
Thank you.
Yeah. So I wanted to first state the main theorem, and then I'll go about the application. And then for the rest of my talk, I'll talk about the proof of the main theorem. So here is the main theorem. Take a new form of weight k for gamma naught of n, a prime p, and a cusp of denominator L. Then first of all, the valuation of f at the cusp C depends only on new form and the valuation of L at P. In particular, it does not depend on the A. So if the cusp is A over L, it does not depend on A. So all the cusps of the same denominator have the same valuation at every cusp. It also does not depend on the isomorphism of QP bar to C. So different isomorphisms really give different valuations on the algebraic integers, but somehow when you look at all the Fourier coefficients, they balance out, and it really is independent of everything else. And then here are the bounds. As I said, you can restrict to L square dividing n. So val P of L could be, without any loss of generality, be assumed to lie between 0 and val P of n over 2. Then the bounds are val P of f/c is bigger than or equal to whatever you see on this slide. So it involves val P of L and val P of n, and there are a few cases. This is what happens in general, but if P is equal to 2, you get a slightly better bounds. So here is what happens for P equal to 2. In that case, you get somewhat better bounds. If you compare, you have actually positive things here, k over 2 plus 1. Whenever k is large, you have strictly positive numbers. So that was really an example we saw on the previous slide, 2 slides ago, where we were getting positive valuations. It's explained by this. That's the main theorem. You might ask, how sharp are these bounds? So we have checked experimentally for new forms attached to elliptic curves that the bounds are completely sharp. I believe for all primes. We checked up to P equal to 23, and then we stopped checking because it seemed kind of pointless, but I'm fairly sure that for all primes and for all new forms of weight 2 over Q, these are sharp bounds. So in general, I'm not 100% sure that they're sharp. There might be some small levels where one could get slightly better, but I think they are generically sharp. Okay, so now coming back to Gergely's question, why was I interested in this question? So the reason we started working on this question is because of this interesting application to the so-called Manin constant. So I now want to explain that application briefly. And since this is a talk on automorphic, the conference on automorphic forms, I won't spend a great deal of time talking about the proof of the application. I'll just go over it. And then for the rest of the talk, I'll talk about the proof of theorem 1. So the Manin constant, what is that? So recall the famous modularity theorem. If you have an elliptic, there are two ways, two more or less equivalent ways of stating that. So given an elliptic curve E over Q of conductor N, the elliptic curve is modular, which means that there will be a new form of weight 2 for gamma naught of N with rational or in fact integer Fourier coefficients such that the Hecke eigenvalues of F are related to the number of points of E over finite fields. So this is the elliptic curve or modular version. The other version is that the elliptic curve has a modular parametrization. That is, there is a surjection defined over Q from x naught of N to E. One could derive each version from the other. Both of these come from this famous modularity theorem of Wiles, Taylor, and the 4 authors who did it in more generality. Note in the second version that this surjection, this parametrization phi, is not unique. So it's common to normalize this parametrization to be optimal, meaning that degree phi to be the least possible as E varies over its isogeny class. And you go over all the possible parametrizations. So now I come to the Manin constant. The Manin constant C of phi is defined to be the constant such that phi star of omega E is equal to C phi times omega F. So what is omega E? Omega E is the well-known Néron differential on the elliptic curve. You pull it back to get a differential on the on x naught of N. And that will, by multiplicity 1, has to be a multiple of omega F, which is just F 2 pi I Fz dz, which is the differential attached to the new form. And the two things have to be multiples of each other, and in fact, rational multiples of each other by multiplicity 1. So that constant is C phi. Maybe for those who, so for those who are not sure what the Néron differential is, maybe it might be useful to just quickly write it down. So if you have elliptic curve, y square is equal to, sorry, not y square. So if you have y square plus a1xy plus a3y is equal to x cubed plus a2x square plus a4x plus a6. So this is kind of a minimal way to write the elliptic curve. Then the omega E on the elliptic curve is simply equal to dx over 2y plus a1x plus a3. This is a fairly canonical way to write down differentials on elliptic curves in the Néron model. So as I said, you can pull it back to the x naught of N, and then the Manin constant is the one that relates that to omega F. Okay. So the question is, what can you say about this Manin constant? In fact, this Manin constant C phi has occurred many times in literature. It is important for computing elliptic curves in the Cremona database. It features in some versions of BSD and in some version of the Gauss-Zagier formula. So it's a very important constant. And the conjecture that Manin made in the 70s is that if you have an optimal parametrization, then C phi has to be equal to plus or minus 1. You cannot do better than plus or minus 1 because you cannot really normalize phi completely. It's only normalized up to plus minus 1. So you can only say that it's equal to plus minus 1. All right, so this is a deep and so far unsolved conjecture with a lot of progress that has been made over the years. So the first thing that one can observe is that C phi is in fact an integer. This is, I believe, first observed by Gaber in his PhD studies. It also occurs in paper of Edixhoven from 1991. And then Abyss and Ulmo showed in 96 that if phi is optimal and P divides C phi, then in fact P divides the level N. So the only primes that can divide the Manin constant are the primes dividing the conductor N. There are further improvements by many authors. I don't want to go over a survey. Also, the conjecture has been computationally verified for many elliptic curves, in fact, up to almost 400,000 conductor. The most useful results for us is the result of Kestutis from very recently that says that if P divides the Manin constant, then in fact, P square must divide N. So in other words, Manin's conjecture is true for square free levels. Also, the only primes that where Manin's conjecture could possibly fail are at the primes whose square divides N. Okay. So by the way, remember that because N is coming from an elliptic curve, we know that the highest power of 2 dividing N can be at most 8, highest power of 3 dividing N is at most 5, and for all of the primes, the highest power of P dividing N is at most 2. So N can't be too bad as far as prime powers go. So this is the theorem that can be proved from our theorem 1, that the Manin constant essentially divides the degree of the map phi. So more precisely, for any level gamma between gamma 1 and gamma 0, possibly including both, and any surjection from x gamma to E, refined over Q, C phi divides 6 times degree phi. And the 6 is a bit annoying, but it can be removed if gamma is equal to gamma 1 of N, or if N is cube free. Or if you assume a general assumption called rational singularities, which is basically an algebraic geometric fact about x naught of N, which is expected to be true, and we know of no counterexamples of that, then in every case, C phi divides degree of phi. So the rough result that we prove is that C phi divides the degree of the map phi. And we think this is really interesting because a priori, degree of phi appears to have nothing whatsoever in common with N. It behaves completely randomly. It is very likely to be co-prime to N, almost as likely to be co-prime to N as two random integers are likely to be co-prime to integers to each other. So basically, there seems to be no apparent connection between the condition P squared divides N, which was proved earlier, and the condition P divides degree phi, which is implied by our theorem. So one could view this as progress towards Manin conjecture, that we complement the previous results by giving a completely different criteria that is forced to be satisfied by primes dividing C phi. So that is the application that comes out of theorem 1. So how does theorem 1 imply theorem 2? I want to give a super brief sketch of why theorem 1 implies theorem 2, because it is really all about arithmetic geometry, and this is just to go over it properly would take me a whole talk. So basically what's going on is that a priori omega f lies in a certain group h naught of x naught n omega 1, where omega 1 is the Kähler differentials. What theorem 1 means is that in fact omega f lies in a certain lattice inside there. And this is exactly where theorem 1 comes in. The fact that it lies in the lattice, and this lattice involves the so-called relative dualizing sheaf, is equivalent to giving certain bounds on periodic valuations of denominators of Fourier coefficients of f at all the cusps. And in fact, theorem 1 gives much smaller bounds than we need for this equation 1. So equation 1 follows. Using this, we can in fact show that omega f lies in an even smaller lattice that involves the Néron model of the Jacobian J naught of n. And now basically using the composition from E to J naught of n to back to E, which is multiplication by degree of phi, you can get the results. So this was obviously very cryptic, and it would take me a very long time to elaborate each of these steps. But the whole point is that denominator bounds, periodic bounds on denominators lead to nice arithmetic geometric facts on where omega f lies, and that you can play with that and derive nice stuff. In the rest of this talk, I'm going to focus on the proof of theorem 1. Any questions? All right, so recall the theorem 1 just gives some bounds on the periodic valuations of Fourier expansions. Okay, so how are we going to do this? So to prove theorem 1, for a cusp C and a prime P, we want to prove good lower bounds on the Fourier expansions of f at the cusp C. The Fourier coefficients of general cusps are very subtle objects. For example, they are in general not multiplicative. So one way to understand them is by the Whittaker model. So if you have f you can idealize it and get an automorphic form phi f from GL2 of A to C, which generates a cuspidal automorphic representation pi. So pi will decompose as a restricted tensor product of pi v, and each pi v is a local representation whose conductor is simply val p of n. The global Whittaker new form is this function wf, which is the integral of a over q of phi f of 1x01g times an additive character, which I fix once and for all, phi of minus x. And this function wf basically packages together all Fourier coefficients at all cusps. That is the key point, that given any cusp C and any Fourier coefficient AF of RC, it will be equal to WF at some explicitly well-defined matrix G. If you want, okay, so that is one relation. You can go from Fourier coefficients at general cusps to this adelic function. On the other hand, what makes this so powerful is that this global Whittaker function will factor as a product of local Whittaker new forms, which are functions purely defined on GL2 of QP or GL2 of R, and they're the local Whittaker new forms, which depends only on the local representation pi v. So they can be studied purely locally. The upshot is that you can decompose the Fourier expansion at a general cusp in terms of these W pi v's at a finite number of places. If you care about the exact relation, one could write it down not very hard. This exact relation occurs in this form in a paper I wrote with Andrew Corbett a few years ago, but it's not hard to derive. It's basically, it's one of the exercises I like to give my first year PhD students. So for a new form of weight k for gamma naught of n, a prime p, and a matrix gamma taking infinity to the cusp c, it will look like AL star star. Then up to a root of unity, AF of RC will be equal to AF of R naught, where R naught is the part of R that is away from n. So you take all the products of primes away from n of whatever divides R. So it's R divided by the GCD of n to the power infinity and R. So this is a Fourier coefficient at infinity, AF of R naught, which, so we understand that they're algebraic integers, times something that you can just write down, a very simple factor, times product over the primes q dividing n of the local Whittaker new form at some specific matrices. So the upshot is that to understand the periodic valuations of AF of R at a cusp C, you really need to understand the periodic valuations of these local Whittaker new forms at these C's. Okay, so that's what I'm saying. So lower bounds for val p of FC reduce to proving lower bounds for val p of W pi at certain matrices. Here, pi q is a representation of GL to QQ. Yeah, I know that's a very bad notation, but I wanted to differentiate between the primes P and Q. They don't have to be the same prime, of course. And you want to understand the periodic valuations here. I should mention that these matrices look a bit random, but they are in fact completely general because any matrix in GL2 of Q has a double coset representative of this form. So it's really trying to understand the periodic valuations of the local Whittaker new form. That's all the question boils down to. This can be viewed as the periodic analog of the local subnorm question of bounding W pi in highly ramified cases. So if you want purely, instead of asking for periodic valuation, you just want to look at absolute values and ask how large can W pi get, then there are a lot of results in this direction. So for instance, Templier proved a lower bound that W pi takes large values if pi is a maximally ramified principal series. This was generalized by me in some papers. And more generally, one can ask for what is the upper bound of W pi in general. And this was solved by Edgar Assing, who managed to give such a bound in all cases. So it is closely related to the question of proving this on the subnorm problem, which we had a talk about. Both lower and upper bounds are very closely related to understanding W pi at its L infinity bound. So what I'm really doing here is a periodic version of that. So how would you approach a question like that? Well, first of all, the values of W pi at diagonal matrices are easy to write down. They basically boil down to Fourier expansion at infinity. So the key point is to access the non-diagonal elements. And to do that, what we do is we refine and extend the method which was developed for the subnorm problem. So this was something that I worked out in a series of papers, and it was further refined by Asing, and it has been used by me for the subnorm question in various setups, by Edgar Asing also for the subnorm question, both for upper bounds. There's also applications to things like Voronoi summation and subconvexity problem. There's a paper of Asing and Corbett. So there's a lot of analytic number theoretic results that were used using this method. And in this talk, I'm going to give a very arithmetic application of the same method. So what is the method? The method hinges on using the local functional equation of Jacobi-Langlands, which basically tells you that if you have this local Whittaker new form, then there is a relation that it satisfies, which allows you to go from the function w to the function 0, 1, minus 1 dot w. So you can translate by this while group element. So the upshot is you can go from diagonal matrices to non-diagonal matrices using this local functional equation. And it involves L factors and epsilon factors. So if you do a bit more work, you basically can write down the local Whittaker new form at any matrix in terms of epsilon factors. So this was formulated by me in what I call the basic identity that writes down W pi as an explicit linear combination of terms using GL2 and GL1 epsilon factors. These epsilon factors are things which are sometimes called the local root numbers. They occur in the functional equation of the local and global functional equations. So, but we are trying to now understand them periodically. So if you're curious what it looks like, here is how it looks like for supercuspidal representations pi. So if you have a supercuspidal representation pi of KGL2 of QQ, then W pi at this matrix that we are interested in is basically equal to a finite linear combination of epsilon factors of GL1 and GL2 representations. Epsilon half of mu is varying over characters of the local field of conductor L with the additional property. And mu inverse pi is the GL2 cross GL1, so a GL2 representation. So for other representations, the basic identity takes a similar shape. So in all cases, you can write down W pi at any matrix as a linear combination of root numbers. The resulting formulas were written down by me in some cases, and then in all cases, they're written down by Edgar in his thesis. So using that, our problem can now be reduced to a very purely local representation theoretic problem of understanding periodic valuations of epsilon factors of representation of GL1Q, QP, and GL2 of QP. So this is, again, I think a very natural question that I don't think has been much studied. So what we do is basically solve this question and then move on to use the basic identity and then solve it for the Whittaker new form. So I want to now give them theorems. First of all, here is the case where Q is not equal to P. If you have a finite extension F local field, non-Archimedean local field of residue characteristic Q, and take a representation of GL2F, which comes from a holomorphic new form, and you take a matrix G, then in fact W pi of G is always going to be always going to only have denominators coming from Q. So it's going to be in Z bar adjoint 1 over Q. So it's not going to have denominators coming from anywhere else. So in particular, if P is not equal to Q, then the periodic valuation is non-negative. One can view this as a purely local version of the Q expansion principle that I said earlier. And probably it can be proved using some kind of global methods, but that is unsatisfying. And what we do is give a purely local proof of this fact. The proof relies on a formula for the Whittaker new vector that goes beyond the basic identity. And it kind of writes down this W pi as some kind of non-Archimedean version of what one might call as 2f1 hypergeometric integrals. This is there in Assing's thesis, and it also appears in unpublished works of Templier and Yukihu earlier. So the proof is really soft of this case Q not equal to P, so I might as well give you the proof. So assuming that such a formula exists, here is a very useful fact. If you have a compact group G and you have a subgroup of finite index whose volume is in some ring R, And now if you take f from g to r to be a k invariant function, then the integral of f over g has to be in r. It's very easy to see this because you can write the integral of f over g as just a sum of integrals of as a sum over g mod k times volume of k, because f is k invariant, and volume of k is in r, and f has values in r, so you get the thing in r. And if I take r to be the ring z bar adjoint 1 over q, then it turns out that the Whittaker new form does indeed have an expression as an integral of this form, and the result follows. A very soft argument which seems to have just worked. So that takes care of the case q not equal to p. So now the question is the case q equal to p. So the problem becomes, if you have a finite extension of qp, try and understand the periodic valuations of epsilon half of mu and epsilon half of mu cross pi, where mu is a finite order character of f cross, and pi is some infinite dimensional irreducible unitary representation of PGL2 of f. By the way, if pi is a principal series, I need to assume that it comes from a global holomorphic new form, because otherwise we can't really expect good results, because one could have all kinds of pi which comes from some random characters where you don't expect any periodic properties. Under these assumptions, it is not hard to see that these root numbers, or these epsilon factors, these local root numbers, are always algebraic numbers of absolute value 1. However, they're not necessarily roots of unity. If they were roots of unity, the problem is trivial because the valuation would be 0 always, but they're not going to be roots of unity usually. They're going to be some random algebraic numbers of absolute value 1. And the question is to understand what are their periodic valuations. The case of GL1 turns out to be not so hard, and it really boils down to the fact that these GL1 epsilon factors are related to classical Gauss sums. For classical Gauss sums, there's a well-known result, or Stickelberger's theorem, that gives periodic valuations. If you use this result and then do some work, you can just write down what the epsilon factor as what's the periodic valuation of epsilon factor is. So here it is. So if you have a finite extension f over qp and a character of finite order, then if the conductor is 1, so if a of chi is the exponent of conductor, sorry, I was using c of chi earlier, but here I'm calling it a of chi, then this is just equal to what I have here. It depends on the residue field of f and its degree over p. So of course, if f is equal to qp, this degree is 1. And that involves this number s chi. So s chi is something that is quite important for us. The way it works is you can write, in this case, chi as a character of a finite field, and then you write it as a power of the Teichmuller character, and you write it in the periodic expansion of that, and the s chi is the sum of the coefficients in the periodic expansion. So it's always going to be between 0 and p minus 1 times the degree. That's an explicit expression for a chi equal to 1. And nicely, if chi is quadratic or a chi is bigger than 1, so whenever the conductor is bigger than 1, then the epsilon factor of the character is always going to be a root of unity. And so obviously the periodic valuation is going to be 0. Any questions so far? So that's the story for GL1. It's very simple result and not that deep. But now let me move on to GL2. So in GL2, you can just classify all the GL2 representations. They are basically of 3 types: principal series, Steinberg twists, and supercuspidals. Of these, the real nasty ones are the so-called non-dihedral supercuspidals, because in every other case, the representations of GL2 come from, in some sense, representations of GL1. They can be in a very precise way induced from GL1 representations, but the non-dihedral supercuspidals don't, but they can only occur if P is equal to 2. So if F has residue characteristic 2. So all of the cases reduce to GL1. So in cases 1, 2, and 3A, we can write the GL2 epsilon factor in terms of GL1, and there's an exact relation in each case. So the problem here reduces to one that we have solved using the previous slide. In the case of 3B, at least over Q2, one can show, in fact, things are not so bad. There are only 16 such non-dihedral representations. So what we do is then we look at the local Langlands correspondence, which tells us that each of these guys come from some representation of the Weil group of Q2 to PGL2C whose image is S4, and we do some work and we can compute all the conductors and all the epsilon factors and so on. And then we use the basic identity, and then we can have an exact formula for W pi of G in every case. And then we check that the bounds that we need are there. So non-dihedral ones we treat separately, and everything else we just boil it down to GL1 cases. And so now we know how to estimate the periodic valuations of GL1 and GL2 epsilon factors. Now remember that the basic identity expresses W pi as an exact finite sum involving the epsilon factors. And using that, we now finally can prove our main local result, which gives sharp periodic valuations of sharp periodic bounds for val p of W pi in all cases. So I don't want to give the full version of our local theorem because it will just be having too many subcases and it will just take many slides. So I just want to give you one special case, just to give the flavor. So here is a special case of our main local theorem. I want to focus on just the supercuspidal representations of conductor exponent at least 2, sorry, strictly bigger than 2. So if P is odd and F over QP is a finite extension, let pi be a supercuspidal representation with trivial central character, then the periodic valuation of W pi at any matrix that we're interested in, and as I remember that these matrices are not special, any matrix can be brought into this form using the by invariance of W pi, then the valuation of that will be greater than or equal to 0 if L is equal to 0 or 1, and it's going to be greater than or equal to the degree of the residue field of F over Fp times 1 minus L over 2 otherwise. So very simple formula in this case, and one that we believe is sharp. But it really involves all the things that I said earlier. So we really had to go over all the epsilon factors, and we in fact have to understand all this Stickelberger's congruence and C chi. There's some structure involving this S chi, which I did not mention. So we really have to understand what they are and do quite a bit of work to get to that theorem. Our main local theorem actually gives such bounds in every case, covers all representations and all conductors and everything, with the caveat that if P equal to 2, then we did not do general local fields, we only did Q2 because things were getting really complicated for extensions of Q2, especially when we look at non-dihedral representations. In fact, for Q2, we get even stronger bounds by getting additional cancellation of the parity involving these epsilon factors because we get them precisely. Now, putting together all this main local theorem, we get theorem 1 as described earlier. So recall that we combine the local bounds on val p of W pi at matrices, given by the general version of our main local theorem, with the earlier equation that I wrote that the Fourier expansion of F at any cusp can be written in terms of these W pi's at these similar matrices. Put these together, and thus you get the lower bounds for val p of F slash C for holomorphic new forms at each cusp C, which was the content of theorem 1. I just wanted to remind you of theorem 1 just because it was right at the beginning. So we get bounds in every case, and for P equal to 2, we get sharper bounds. And the sharper bounds for P equal to 2 basically comes from the fact that our local theorem at P equal to 2 is in fact sharper because we actually were able to get some additional periodic and two-adic cancellation using the fact that epsilon factors were like 1 and minus 1 or 1 and 1 and add to give 2 or things like that. So we get powers of 2 there. So that was the main local theorem. Okay, I think that's all I wanted to say. Thank you.
Thank you very much. Are there questions? There is a question in chat.
Let me try to see the chat. Can you derive theorem 1 from Manin's conjecture? No, because, oh well, it's not clear to me. I don't think so, because Manin's conjecture implies certain bounds on the Fourier expansions at F at each cusp, as I told you, but those bounds are weaker than theorem 1. So we get even a much worse version of theorem 1 would have given the application to Manin's conjecture that we prove, but the full Manin's conjecture does not seem to give, or does not appear to relate to stronger bounds? So I think the answer is no. This is really stronger than whatever Manin conjecture would need.
I also have a question. In one of the examples, you showed some unexpected congruences for Fourier coefficients of modular forms at other cusps. Are there applications in this direction of this theorem? I mean, can you prove congruences for Fourier expansions of cusp forms?
Let's go back. Sorry, let me go back to the slides of the example. Yeah. So what are the unexpected ones?
Sorry?
So sorry, what are the unexpected congruences that you are mentioning here?
So in that case, when the Fourier coefficients were integers divisible by some prime above in a quadratic extension.
Yeah.
Yeah,
Yes.
in this slide, yeah.
Yeah.
So all the coefficients there are, to me, surprisingly divisible by a prime above 5.
That is
The first example.
well, that is forced by our main theorem actually, because our main theorem in this case would say that the valuation is bigger than or equal to -12. So if it was not true, then our theorem would be false. So somehow it's
actually implied
our theorem. Yeah, so our theorem forces this to happen.
Yeah, so there may be interesting applications to such congruences, which I think are unexpected.
Yeah, sure. Yeah, I mean, the thing to keep in mind though is that I wrote it down in this form, but in general, you don't expect them to be rational numbers. So if you write it down, if you write down algebraic numbers as like a rational denominator, then you will always have usually some appropriate prime ideas on the top. So yeah, possibly they would lead to something nice. On the other hand, if the valuation is -12 or anything fractional, it would always be of this form. So I don't know how to really interpret this. But yes, the fact that the valuation here is -12 and not say -1 is crucial to our application to Manin's conjecture, because for Manin's conjecture in this case, we need a bound to be bigger than or equal to -4/5 actually. So or maybe it was, yeah, -3/4, I don't remember. So -1 would not have given us the application. So we really needed something strictly better than -1 for the application to Manin's conjecture. And that really boils down to this fact that omega f in the arithmetic geometric sense lies in this smaller lattice. It is essentially equivalent to that.
That's very nice.
Okay. Any
Other questions?
Yeah, hi Abhishek. So I have a, so you said at some point that some special values of this Whittaker new form look like or come from some hypergeometric series.
Yes.
So how those hypergeometric series look like? Can you tell us like briefly or something?
Yes. So they basically would look like, okay, let me try to remember exactly. Basically they would involve an additive and a multiplicative character with some quadratic things inside. I forget the exact formula. So,
I mean, for instance, the coefficients are like local L values or something, like in hypergeometric series over Archimedean place.
Sorry, when I say hypergeometric function, I mean like if you have the 2f1 hypergeometric function, that involves, what does it involve? It involves some exponentials, and it involves some, which correspond to additive character, and it involves some thing that is corresponding to multiplicative, like a powers, and then you take an integral, right? That's like the integral representation of a 2f1 hypergeometric function in the classical sense. What I mean here is it's a periodic version of that. So you are going to get something like something probably similar. So you're going to get an integral which probably looks like an integral over some local field. Maybe you take an extension of FOE, and then you take maybe an additive character psi, and you do something of norm of some something involving x plus whatever and then you take a additive character that involves something like some other function of x. So, sorry, and then you take the norm. So there's a quadratic thing here in the psi, and then you have a chi. So there's an additive character with a quadratic thing inside and the multiplicative character, and take the integral. So that's what I mean by having a expression like a 2f1 hypergeometric function.
I see. So does it kind of follow from Jacques' integral formula?
So basically what you need to do is, it does not follow in obvious way from any of those formulas as far as I see in the p-adic case. There are multiple ways to derive a formula like that. One way is to use the basic identity. So I'll go back to the basic identity for a moment. Let me show you what the basic identity looks like, for instance, for supercuspidals. So here you see the formula involves a sum of epsilon factors, right? But the epsilon factors themselves can be written as integrals, because if it's, in most cases, these epsilon factors boil down to GL1, Gauss sums, and those are integrals over p-adic fields, right? So there's a sum and an integral, and you change the order of summation and you do some tricks and it end up getting a real integral. So it is really using some additional structure here. It is not immediate. So that is one way to derive this. Another way to derive this, in the case of principal series, for instance, which was done in Tamplier in his unpublished thing, is that you can take a intertwining map from the induced representation to the Whittaker model, and you can do something like that. So there are multiple ways to derive it. So some formulas like this appear in some unpublished works of Nicolas Tamplier and in Yuki Hu, but in all cases, it's there in Edgar Ising's thesis. So that's, so if you just look at his thesis or his paper in Transactions, there are formulas that give a very compact expression. And there's really, we're really using additional structure here, which is quite powerful, I think.
Okay, thanks.
Yeah, there is another question from the chat. Given Cremona's algorithm to compute degree of phi, can you formulate any conjecture to escaping cases of proving Manin's conjecture? I don't quite, sorry, I can't quite understand the question. What do you mean by escaping cases? Okay, if the person is, okay, so as far as I know, we cannot formulate any new that do not follow from the divisibilities. So I don't quite know what this means. So as I said, the conjecture is always that the C phi is equal to 1. So we believe that C phi is 1. So that would be the most obvious conjecture. So what we are doing is we can of course get new cases of Manin's conjecture. So assume that Cremona did not do any of his work of proving of checking Manin's conjecture, then our theorem would verify Manin's conjecture in a host of new cases. Because square divides n, the two things will have nothing to do with each other. And in every such case, our theorem proves that Manin's conjecture is true. So we experimentally check that in about 20 or 30% new cases, or maybe I forget what percent, but in some substantial number of new cases, maybe it was 40%, we get Manin's conjecture just from our theorem. So maybe that's not so interesting, but it just shows that there are two orthogonal criteria. P square divides n. If P divides C phi, then P square has to divide n. If P divides C phi, then P has to divide degree of phi. The two conditions are kind of random with respect to each other. So typically you would expect in many cases they're not to intersect. And so C phi would be forced to be 1 in many new cases. But I don't think we can formulate any new conjecture unless I'm kind of misunderstanding this question. What is the other question? When GCD of degree phi n is not square free. Yeah, there are cases when GCD of n, degree phi of n is not square free, because if it was square free, we have basically, basically if GCD of degree phi n is not square free, things are nice. It's not square free, there are examples when that happens. They seem to happen somewhat randomly and mostly happen at the primes 2 and 3, because at other primes, you remember that p, the highest power of p dividing n can be at most 2 if p is bigger than or equal to 5. So you would nearly need p squared to also divide degree of phi. It could probably happen, but it would happen by coincidence, really. So on rare equations, it will happen, but usually it doesn't. It does happen at 2 and 3 a bit more, because at 2 and 3, n can have powers of 2 and 3 that are up to 8 and up to 5 respectively. So, and degree of phi can be even quite often at about half the cases. That is one case where the randomness is lost. So, but yeah, there are examples when that happens, but it seems to be fairly random.
Thank you. Are there other questions?
Hi, may I ask? Hello?
Yeah. Hi, Janine.
Hi, Abhishek. One moment. Yeah, beautiful lecture. Thanks. A couple of general questions. First, could you say a little bit more about how the first step of the proof works? Second, what do you know or what is studied about the p-adic valuations of the local epsilon factors in higher rank case? Is there anything? And that's it.
Okay, great question. Sorry, the first question, which step of the proof did you want me to talk about?
The first step with the relative dualizing sheaf.
Okay, the arithmetic geometry part. Let me go back. Yeah, so that's the part obviously I didn't talk anything about, because this is a conference on morphic forms, and also if I were to go over that, sorry, where did I go? Here it is. I would take the whole talk. Also, this is the part which is not really my expertise, but I'll do my best.
Okay, maybe I should unask the question or ask you privately.
I'll do my best. So let me just go to the whiteboard again. Did people see my whiteboard the last time I tried to do that, right?
Yeah.
Might be easier to just write down for you.
Yeah, sure.
Okay, how do I scroll down on the whiteboard? Oops, so maybe I'll just clear all drawings because, okay, so what happens is that, so omega 1 is of course the Kähler differentials, that's the common notation. So omega is the relative dualizing sheaf. So it is kind of like omega 1. Sorry, did you say anything about omega, or do you want me to go? Do you know what the relative dualizing sheaf is, or do you want me to say a little bit about that?
Just a quick sketch. I mean, it's
a quick sketch. Okay, so omega of x naught n over z is basically going to be equal to omega 1 of u over z, where u is any z smooth open set inside x naught of n. So it kind of behaves similar to omega 1, but the point behaves much nicer at the non-smooth point. So that's why we replace omega by omega 1. And the thing that we really care about is that h naught of j naught of n, everything is over z here, of omega 1 happens to be equal to h naught of x naught of n over omega. That is the key point. So ultimately we care about j naught of n because of the last step and omega 1, but that seems completely inaccessible to us, because here j naught of n is a Néron model of j naught of n. What we do is we use this very useful fact that we can go to omega and then we go back to x naught of n, and then we need to understand about this and to check that omega f belongs here can be checked prime by prime. That boils down to p-adic valuations, and in fact is equivalent to satisfying conditions and p-adic valuations of Fourier expansions at different cusps.
Yeah, but that's exactly what I wanted to know. Thank you.
All right.
Nice explanation. And for the epsilon factors,
epsilon factors. For the epsilon factors, to be honest, I don't know anything that is known. Of course, if you have a general GLN automorphic representation, sorry, not automorphic, GLN local representation, and let's say it's supercuspidal, because if it's principal series, I don't expect any reasonable results unless you assume it's coming from some algebraic automorphic representation or something.
Absolutely.
Let's say cuspidal guy of GLN, and you want to know its p-adic valuation. I don't know any results in general. I mean, okay, if pi tells dual, it's plus or minus 1, so there's nothing to worry about. So we really care about non-trivial central characters. So I don't really know anything. I don't know any results in that direction.
When it comes from when it comes from a global cohomological representation, you wouldn't expect.
Yeah, it would, and even then, I mean, okay, but that doesn't help me very much.
No, not for this problem. But
yeah, almost supercuspidals would come from something like that, and I think one could do something similar. For instance, at least if the supercuspidal is in some sense coming from, or if the representation comes from lower rank groups, one could do an inductive procedure and try to understand. It's a very interesting and I think very natural question, which I would love to work on at some point, but I don't know any results of that. So.
Okay, thank you. And beautiful talk again.
Thank you. Is there another question?
Yeah, I have a question.
Yes.
Hi, Abhishek.
Okay.
I think you said that it was in like your F has like central character, trivial central character. Is there any way of like trying to like generalize it to a non-central character?
Absolutely. You could do everything for non-trivial central character. The formulas get really messy. So that's because I hid a lot of things under the carpet here in my proof. I just want to go to one particular thing which I basically said it follows. So let me just go there. Here. So we get the periodic valuations of epsilon factors, the basic entity explicit as an explicit finite sum, and using that, you just get our main local result. This step is actually quite non-trivial. It involves a horrible amount of computations with many, many cases, checking the expressions which are quite nasty. If you just look at the actual expressions, for instance, Edgar's paper, you would know, and you have to check like a million subcases. So it was like 6 pages of very dense calculation to just go from part 2 to part 3. And if we were to do non-trivial central character, there's no obstruction theoretically, but those 5 pages would be like 15 pages, and it was not needed for application, so we just did not do it. It would be a nice problem for a PhD student.
Okay, thanks.
Other questions? It seems not then. Thank you again.
All right, thank you.
Then I stop recording now.